Welcome, my friend. You found your way to the Sleepy Scientist, a quiet corner of the internet where curiosity moves at a gentle pace and the stars above are always within reach. I'm so glad you're here. Before we set off on tonight's journey, may I ask, where in the world are you watching from? I always find it fascinating to imagine this little community stretching across continents, connected by a shared moment under the same sky. If you're new here, I'd be grateful if you could give the video a like and consider subscribing so you can join us again for more gentle explorations of the universe. And if you'd like to know the moment our next Sleepy Science adventure drifts into your feed, you can tap the little notification bell. To those who have already subscribed, thank you for being part of this strange and wonderful experiment in bedtime science. Now, I do hope this video isn't too interesting and ends up keeping you awake, though. If it does, at least you'll drift off with a few more facts in your mind than you had when you pressed play. It's the kind of problem I'm not entirely sure I should apologize for. Tonight, we're going to take a slow, starlit voyage through our galaxy, the Milky Way. But here's the question I'd like to begin with. If we can only ever see our home from the inside, how can we truly know what it looks like? The Milky Way is not just a backdrop to our lives, is the very stage upon which all of human history, all of life, and every shimmering moment has played out. We live within its vast embrace, yet most of it remains invisible to our eyes, hidden behind clouds of cosmic dust and the sheer dizzying scale of space itself. In this journey, we will drift slowly from the familiar to the far-flung. We'll wander the spiral arms, linger among newborn stars, cross the quiet halo, and dip into the mysterious heart of the galaxy where a supermassive black hole resides. Along the way, we'll meet the many kinds of stars that call this galaxy home, the clusters they form, and the gas and dust that both obscures and creates them. We will explore not only what the Milky Way is made of, but also how we know what we know. The careful observations, the patient measurements, and the ingenuity that allow us to map something so impossibly large from our tiny vantage point. And perhaps we will think about what this galaxy means to us culturally, scientifically, and personally, as the only cosmic neighborhood we've ever known. So get comfortable, let your thoughts drift like starlight through the darkness, and join me as we begin our slow voyage through the Milky Way. If you could step far enough away from our galaxy, far, far beyond the pull of its stars, you would see it as a soft glowing whirlpool hanging in the dark. From that impossible vantage point, the Milky Way would reveal itself as a vast barred spiral, a flattened disk of stars wrapped around a bright central bulge, with long arms curling gracefully outward like the petals of a cosmic flower. It is a place of both order and chaos, where patterns emerge from countless random motions, and where light from billions of suns blends into a single pale shimmer. The scale of it is almost absurd. From end to end, the Milky Way stretches for roughly 100,000 light-years. A light-year is the distance light can travel in 1 year, about 912 trillion kilometers, which means the galaxy is wide enough that even at light speed, a trip from one side to the other would take longer than the entire history of human civilization by a factor so large it makes numbers feel slightly ridiculous. If our sun were the size of a single grain of sand, the galaxy would still be larger than the span of entire continents. Its shape is not simply a neat spiral drawn in space. At the heart lies a bar-shaped cluster of stars running through the central bulge. From the ends of that bar, the spiral arms unwind, rich with gas, dust, and newly formed stars. The main arms, Perseus, Scutum, Centaurus, Norma, and Sagittarius Carina, sweep outward in gentle arcs. Between them lie shorter segments and spurs like smaller branches in a great cosmic tree. From above, it would look like an artist's slow brushstroke through the night spiraling ever outward. We rather modestly do not occupy one of the grand sweeping main arms. Instead, our solar system sits in a quieter neighborhood, a smaller spur of stars called the Orion Arm, or sometimes the Orion Spur. This spur lies between two larger arms, the Sagittarius Arm closer to the Galactic Center, and the Perseus Arm farther out toward the edge. Our location is, in many ways, rather fortunate. It is calm enough to avoid the more chaotic regions of intense star formation that might bathe worlds in harmful radiation, but close enough to the action that we're surrounded by a rich view of stellar life. From our position, we are roughly 27,000 light-years away from the Galactic Center. That might not sound too bad. After all, in everyday human terms, 27,000 of anything is not an unthinkable number. but in space, it is an immense gulf. If you could somehow travel at the speed of light, which you cannot unless you are light, it would still take you 27 millennia to get there. For comparison, 27,000 years ago, the last ice age was in full swing, and mammoths were still trudging across the Earth. This vastness also means that our nearest stellar neighbors are anything but next door. The closest star system to our Sun, Alpha Centauri, is more than 4 light-years away, around 40 trillion kilometers. Even with our fastest spacecraft, it would take tens of thousands of years to get there. In galactic terms, that is like saying the house next door is actually somewhere past the edge of the horizon, and to get there, you would need to walk for multiple human lifetimes without stopping. The Milky Way's disk is not perfectly flat. It has a gentle warp as though the whole galaxy has been very slowly twisted over time. This warp is thought to be caused by gravitational interactions with neighboring satellite galaxies, smaller companions that orbit the Milky Way much as the Moon orbits Earth. The disk is also surprisingly thin compared to its width, like a cosmic pancake with a fluffy central mound. Most of the galaxy's stars, gas and dust, lie within a disk only a few thousand light-years thick, while a halo of old stars and dark matter surrounds it in all directions. This halo is the galaxy's ghostly outer boundary, and though it is far less dense than the disk, it holds important clues about the Milky Way's history. Within it are ancient globular clusters, spherical swarms of stars that have been orbiting the galaxy for billions of years, predating much of the structure we see today. These clusters drift far above and below the galactic plane, marking the Milky Way's oldest stellar population. The sheer number of stars in the galaxy is staggering. Estimates suggest there are at least 100 billion of them and possibly as many as 400 billion. And yet the space between them is so vast that on average the nearest star to any given star is several light-years away. In a way, the Milky Way is more emptiness than substance, an enormous expanse in which islands of light float in oceans of darkness. From our small patch within the Orion Arm, we cannot see the Milky Way as an outsider would. Instead, we experience it from within as a river of pale light stretching across the night sky. That light is not the glow of a single object, but the combined radiance of countless stars too distant to resolve individually, their light blending into a misty band. It is one of the few things in nature that is both an intimate part of our world and unimaginably far beyond it. Understanding the Milky Way's shape, size, and structure is like trying to sketch the floor plan of a house while standing inside a single room with no windows. We must piece together the whole from small glimpses, relying on careful measurement, the behavior of light, and the slow mapping of the sky. Every star's position, every swirl of gas, every faint whisper of radio waves tells us a little more about the home we live in. A home so vast that our entire civilization is a barely noticeable flicker within one of its countless stars. And yet, despite its size, the Milky Way is still just one galaxy among billions in the universe. From the outside, it might not seem particularly special, but from here inside it, it is everything. The stage, the scenery, and the quiet backdrop to our every moment. If you could see the Milky Way from far above, you would notice it does not form a perfect pinwheel of evenly curved arms. Instead, there is something striking at its center, a bright bar of stars cutting across the bulge from which the great spiral arms unfurl. This makes the Milky Way what astronomers call a barred spiral galaxy. The bar is not just a decorative feature. It is thought to act like a gravitational engine channeling gas inward toward the center, feeding both new star formation and the activity around the supermassive black hole that resides there. In turn, the bar's rotation helps shape and maintain the galaxy's spiral pattern, guiding material into the arms like water flowing into a whirlpool. The spiral arms themselves are not solid structures the way an actual whirlpool's currents might be. They are regions where stars and gas are more densely packed than in the surrounding space. But individual stars do not stay in the same arm forever. Instead, the arms are more like traffic jams on a cosmic scale. Cars in a traffic jam move in and out, but the jam itself persists in roughly the same place. Similarly, stars, gas, and dust pass through the spiral arms, slowed and compressed by a kind of gravitational wave pattern known as a density wave. This density wave theory explains why the spiral arms are the cradles of so many young stars. As gas clouds drift into an arm, the added pressure from the denser environment causes them to collapse, igniting new stars. The brightest and most massive of these stars live fast and die young, burning through their fuel in only a few million years. Because they do not have time to wander far from where they were born, these luminous giants light up the spiral arms, tracing their curves for us to see from within. Meanwhile, older and smaller stars drift out of the arms, continuing their slow orbits around the galactic center. If we could take a slow and unhurried tour from arm to arm, starting near our own Orion arm, we would find each one has its own character. The Orion arm is more of a spur than a full arm, but it is by no means unremarkable. It contains not only our sun and solar system, but also familiar landmarks of the night sky, such as the Orion Nebula and the Player D star cluster. This is the view we know best, but in cosmic terms, it is just a small side street off a grand galactic boulevard. Move inward toward the Galactic Center, and you encounter the Sagittarius Arm. This arm is a rich hub of star formation filled with bright nebulae, like the Lagoon Nebula and the Trifid Nebula, as well as star clusters only a few million years old. Its close proximity to the dense central regions means there is a steady supply of gas being funneled into it, giving it a vibrant, energetic quality. From our perspective on Earth, looking through the Sagittarius Arm is one of the best ways to see deep into the Milky Way's core. Traveling outward from our spur instead, you would cross the gap to the Perseus Arm. This is one of the Milky Way's two main arms, stretching in a long, graceful curve that is home to some of the galaxy's largest star-forming complexes. The Perseus Arm is rich in both young, massive stars and the glowing clouds of hydrogen gas that mark active stellar nurseries. Radio telescopes have traced giant molecular clouds here, each containing enough material to form thousands of new stars. It is the galactic equivalent of an agricultural heartland, a place where new generations are continually being sown and grown. Farther in toward the galactic center lies the Scutum Centauris Arm, another of the main arms, sweeping from near the bar outward across much of the galaxy's inner disk. It is home to some of the largest and brightest star clusters known in the Milky Way, including Westerland 1, a dense collection of massive stars packed into a relatively small region. The Scutum Centauris Arm is so rich in luminous stars that it outshines many other parts of the galaxy. Though from our position in the Orion Spur, it is partly veiled by clouds of interstellar dust. Beyond that lies the Norma Arm tucked deep within the inner regions of the galaxy. This arm is harder to observe directly because we view it through thick curtains of gas and dust, but infrared and radio observations reveal its wealth of young stars and its role as one of the key structural components of the Milky Way. In many ways, it is a reminder that our view of the galaxy is always partial. There are wonders we know exist but can never fully see with human eyes. What makes this spiral structure so remarkable is that it is not a fixed arrangement carved in stone, but a pattern that persists over billions of years. Despite the motion of countless individual stars, the entire galaxy rotates. The Sun itself orbits the galactic center once every 225 million years or so, but the arms remain as stable, overarching features. This balance between motion and structure gives the Milky Way its elegance, a grace that is both dynamic and enduring. The bar at the center, the arms winding outward, and the spaces between them all work together to define the Milky Way's shape. The spaces between the arms are not empty. They are filled with stars, and sometimes even faint, less active clouds of gas. But the arms are where the galaxy shows off, where it concentrates its most photogenic displays of glowing gas and brilliant short-lived stars. And yet, despite the beauty of the arms, from the inside, they can be surprisingly difficult to recognize. On Earth, when we look up at the Milky Way's band across the night sky, we're seeing along the plane of the galaxy a dense concentration of stars and dust that hides the exact arrangement of the arms. Mapping them has been like trying to chart the streets of a city while standing in the middle of one. We rely on the positions of known objects, on measurements of their distances and motions, and on the faint whispers of radio waves from hydrogen atoms spread through space. Piece by piece, these clues have allowed astronomers to outline the grand spiral form we cannot see directly. In the end, the Milky Way spiral is more than just a pretty shape. It is the pattern of its life. The arms are where stars are born, where the galaxy's raw materials are recycled into new generations, and where light and color spill most vividly into the cosmic night. To drift from one arm to another would be to pass through regions of quiet starlight into bustling star-forming hubs and back again, each with its own rhythm. each a part of the galaxy's endless, slow-turning dance. At the heart of the Milky Way lies a region unlike anywhere else in our galaxy, the Galactic Center. From our position in the Orion Arm, it is hidden behind vast curtains of dust and gas, invisible to our eyes, even on the clearest night. Yet astronomers have peered through those curtains using infrared and radio waves, revealing a place of staggering density, ancient stars, and gravitational forces so extreme they defy everyday experience. The Galactic Center is dominated by a swollen bulge of stars, a dense football-shaped concentration that extends thousands of light years above and below the galactic plane. This bulge contains some of the oldest stars in the Milky Way, many of them low in heavy elements, which suggests they formed in the galaxy's earliest days. The sheer number of stars here is hard to grasp. Imagine the night sky. If every star you could see was suddenly packed into a space a fraction of its current size. From within the bulge, the sky would be so crowded with light that true darkness might be rare. The combined glow of millions of suns turning night into a perpetual dim twilight. But it is not just a stellar crowd. Nestled deep within this throng is perhaps the most intriguing resident of all, Sagittarius, a star, the supermassive black hole at the center of the Milky Way. Its name comes from its position in the sky in the direction of the constellation Sagittarius. And the A star is an astronomer's way of marking it as something special. Despite its immense mass, about 4 million times that of our Sun, Sagittarius A is surprisingly quiet most of the time, radiating only faintly compared to the raging matter-devouring black holes at the centers of some other galaxies. We cannot see Sagittarius a star directly because no light can escape its grasp, but its presence is revealed through its influence on the stars around it. In the late 20th century, astronomers began tracking a group of stars very close to the galactic center. These stars, known as the SARs, were seen whipping around an unseen point at extraordinary speeds, some completing full orbits in just over a decade. Only an object with the mass of millions of suns packed into a space no larger than our solar system could explain such motion. And that object could only be a black hole. One star in particular, called S2, has been a star of the show, so to speak. It swings in closer to Sagittarius, a star than Pluto is to our Sun, reaching speeds of thousands of kilometers. At those distances, the gravitational pull is so intense that the predictions of Einstein's general theory of relativity come into play. In fact, careful observation of S2's path has confirmed subtle effects predicted by relativity, such as the way light is redshifted by strong gravity. These stars are not just beautiful, they are living laboratories for testing our understanding of the universe. The environment near the galactic center is extreme in almost every sense. The density of stars increases dramatically as you approach the middle, meaning stellar encounters are far more common. Massive young stars can be found here as well. Even though it might seem like the last place you would expect them, the region is turbulent, bathed in intense radiation, and crowded with gravitational influences. Their very presence suggests that star formation can occur in conditions far harsher than those we find in the galaxy's quieter suburbs. Gas and dust clouds swirl through the center, occasionally falling toward the black hole. When enough material gets close, it forms an accretion disk, a whirling maelstrom of gas spiraling inward, heating up to millions of degrees and emitting bursts of energy. These feeding events are sporadic for Sagittarius A, but they remind us that even a relatively calm, supermassive black hole is not entirely dormant. Astronomers have also found evidence of massive outflows from the galactic center in the past, such as the Fermi bubbles, enormous lobes of high-energy radiation extending tens of thousands of light-years above and below the disk, possibly caused by ancient eruptions from Sagittarius, a star. There is also a population of enigmatic objects here, some of which appear to blur the line between stars and gas clouds. They may be stars enveloped in thick shrouds of dust or something stranger. Still, in the gravitational chaos near Sagittarius, a star matter can be stretched and heated to the point where familiar categories break down. Even with our best instruments, the galactic center remains a place of mystery. We can trace the orbits of stars and map the distribution of gas, but the sheer density of material makes it difficult to get a clear picture. It is a reminder that our view is always from within, peering through a crowded, turbulent foreground toward the hidden core of our home. If you could stand safely on a stable platform close to Sagittarius, a a purely hypothetical notion. Since gravity there would tear apart anything solid, the sky would be unlike anything imaginable. Stars would whirl past in fast arcs, distorted by gravitational lensing into strange smears and loops of light. The black hole itself would not appear as a hole so much as a dark circular void, framed by a glowing ring where light is bent and captured from the surrounding stars. The scale and speed of motion would make the whole scene feel more like the inside of some vast cosmic machine than the serene night skies we know. And yet, for all its extremes, the Galactic Center is part of the same galaxy that gently cradles our sun. The pull of Sagittarius. A star reaches us even here, guiding the sun and its planets in their long, slow orbit. From our quiet vantage point, it is easy to forget that at the core of our galaxy lies a place where space and time are bent into shapes that defy everyday intuition. A reminder that the Milky Way is as much a place of extremes as it is of quiet beauty. The Milky Way is not just a collection of stars. It is a vast, glittering archive of every kind of star nature has ever devised. From tiny, cool red dwarfs to enormous, short-lived supergiants, from the steady hum of main sequence stars to the exotic remnants of dead suns. Our galaxy contains a full cast of stellar characters, each with its own story. If you could float through the galaxy without hurry, you might pass by millions of stars in every shade and size, their light ranging from deep crimson to piercing blue-white. Most stars you encountered would seem quiet and unassuming, the cosmic equivalent of people who keep to themselves and rarely make headlines. But scattered among them would be rare giants, brilliant and unpredictable, their lives burning fast and ending with spectacular finales. Astronomers often sort stars using the Hertzsprung-Russell diagram, a kind of map that plots them according to brightness and surface temperature. Most stars, including our sun, fall along a band called the main sequence. Here, stars are in the stable phase of their lives, steadily fusing hydrogen into helium in their cores. The position of a star on this sequence depends largely on its mass. Heavier stars are hotter, brighter, and bluer, while lighter stars are cooler, dimmer, and redder. The smallest and most common of these are the red dwarfs. They are so faint that none are visible to the naked eye from Earth. Yet they make up the overwhelming majority of the Milky Way's stellar population. A red dwarf's life is one of quiet efficiency because they burn their fuel slowly. They can shine for trillions of years, far longer than the current age of the universe. In a sense, they are the ultimate survivors, small, steady, and built to last. If the galaxy had a background soundtrack, it would be the faint, enduring hum of red dwarfs. At the other end of the main sequence are the massive hot blue stars. These luminous giants are rare but impossible to miss. Their intense light can travel great distances, and they often dominate the regions around them. But their brilliance comes at a cost. They burn through their nuclear fuel at a furious rate, living only a few million years before running out and ending their lives in spectacular supernova explosions. For a galaxy, these stars are more like dazzling fireworks than long-burning candles. Between these extremes lies a wide variety of stellar types. Yellow dwarfs like the sun, orange dwarfs slightly cooler and dimmer, and white stars that burn hotter. Each one will spend the majority of its life on the main sequence in a long period of balance between the outward pressure of fusion and the inward pull of gravity. This balance is so stable that from our perspective, stars in this stage seem almost eternal. But not all stars are content to remain in the main sequence forever. When a star exhausts the hydrogen in its core, it begins to change. For stars like the sun, this means swelling into a red giant, a cooler but much larger star whose outer layers expand dramatically. A red giant can be hundreds of times wider than the sun, its surface glowing with a soft orange-red light. The atmosphere becomes so distended that the outer layers can drift away into space, enriching the galaxy with heavier elements forged in the star's core. More massive stars follow a different path. When their hydrogen runs out, they move rapidly through a series of fusion stages, creating heavier and heavier elements until they reach iron, a dead end for energy production. At that point, the core collapses under its own gravity, triggering a supernova. The aftermath can leave behind either a neutron star, a city-sized object so dense that a teaspoon of its material would weigh billions of tons, or for the most massive stars, a black hole. Neutron stars are among the strangest objects in the galaxy. Some spin rapidly, sweeping beams of radiation across space like lighthouse beacons. These pulsars can be detected from thousands of light years away. Their signals as regular as the ticking of a clock. Others are magnetars with magnetic fields so intense they could erase the data on every credit card on Earth from a distance of several 100,000 km. Not that they're in any rush to do so. Supergiants are the most flamboyant of all stars. These immense bright behemoths can be tens to hundreds of times the mass of the Sun and thousands of times more luminous. Betelgeuse in the constellation. Orion is a well-known red supergiant, large enough that if placed in the center of our solar system, its surface would extend past the orbit of Mars. Blue supergiants like Riel are equally impressive, but live even shorter lives. Their powerful stellar winds can shape the surrounding space, carving cavities and interstellar gas and creating spectacular nebulae when they eventually explode. There are also the stellar elders, white dwarfs, the remnants of sun-like stars that have shed their outer layers and no longer fuse elements in their cores. These dense Earth-sized objects slowly cool over billions of years, fading into black dwarfs, a stage the universe has not yet reached because it is not old enough for any white dwarf to have cooled that far. Every type of star plays a role in the Milky Way's ecology. Massive stars seed the galaxy with heavy elements in their violent deaths, enriching the gas from which new stars and planets will form. Smaller stars preserve those elements over long timescales, acting as stable hosts for planetary systems. The constant cycle of birth, life, and death ensures that the galaxy remains a dynamic, evolving place rather than a static one. If you are drifting through space, moving slowly from one star to the next, you might notice patterns in their distribution. Clusters of hot young stars often lie near regions of active star formation, glowing against the dark backdrop of molecular clouds. Farther away in the quieter reaches, the view is dominated by older, cooler stars, red dwarfs and orange dwarfs, their light softer and steadier. This balance between the rare brilliance of giants and the quiet persistence of dwarfs gives the Milky Way its character. Perhaps the most humbling realization is that the stars we can see with the naked eye represent only a tiny fraction of those that exist. The vast majority, the countless red dwarfs scattered throughout the galaxy, shine too faintly for us to notice without a telescope. And yet, in sheer number, they dominate, forming the unseen backbone of the Milky Way's stellar population. They may not dazzle the eye, but their quiet endurance means they will still be here long after the last supergiant has burned out, their light continuing to fill the galaxy's night for trillions of years to come. Among the most beautiful and mysterious places in the Milky Way are the stellar nurseries, vast clouds of gas and dust where new stars are quietly taking shape. These regions are not hurried. The process of creating a star can take millions of years, unfolding with a patience that only the cosmos can manage. Seen through a telescope, these nurseries often appear as glowing, intricately patterned nebulae, each with its own character and history. Nebula are essentially enormous interstellar clouds, often dozens or even hundreds of light years across. They're composed mainly of hydrogen gas with smaller amounts of helium and traces of heavier elements. Mixed in with the gas is fine dust, tiny grains of carbon and silicates that scatter and absorb light. This dust is not like the kind that gathers under your bed. Each particle is far smaller than a grain of sand, yet together they can block the light of distant stars, creating dark patches and shapes against the glowing background of the galaxy. One of the most famous stellar nurseries is the Orion Nebula, a bright patch in the sword of the constellation Orion that can be seen with the naked eye from Earth. Just over 1,300 light-years away, it is the closest region of massive star formation to our solar system. Within its glowing clouds lies a cluster of young hot stars known as the trapezium, whose intense radiation lights up the surrounding gas. The Orion Nebula is like a cosmic classroom, allowing astronomers to study the process of star birth in detail. Its filaments and knots of gas reveal where gravity is slowly drawing material together, where new stars are forming, and where stellar winds from older siblings are shaping the landscape for the next generation. Farther away in the southern skies lies the Carina Nebula, one of the largest and most active star-forming regions in the Milky Way, stretching over 300 light-years across. It contains some of the most massive and luminous stars known, including the volatile giant ETA. The Carina Nebula is a turbulent place with powerful stellar winds and supernova explosions sculpting its clouds into dramatic shapes, towering pillars, rippling arcs, and vast cavities blown clear of gas. These processes both destroy and create. They disperse gas in some places while compressing it in others, triggering the birth of new stars. Another striking example is the Eagle Nebula. Made famous by the Hubble Space Telescope's image of the Pillars of Creation, these towering columns of gas and dust, each several light-years tall, are active sites of star formation. At their tips, small clumps of dense material called evaporating gaseous globules are collapsing under gravity, soon to ignite as newborn stars. The name Pillars of Creation is no poetic exaggeration. They are literally sculpting and giving rise to new stellar systems. Over time, radiation from nearby hot stars will erode the pillars away. But by then, many of the stars they nurtured will have already emerged into the wider galaxy. The process of starbirth begins in the coldest, densest regions of these clouds. When a pocket of gas becomes dense enough, its own gravity begins to pull it inward. As it collapses, the material at the center heats up, forming a protoar. This is a delicate stage when the young star is still shrouded in its birth cocoon of dust and gas, visible only at infrared wavelengths. Over thousands to millions of years, the protoar gathers more material from its surroundings, growing in mass. When the temperature and pressure in its core become high enough, hydrogen fusion begins and the star officially joins the galaxy's stellar population. The environment of a stellar nursery is far from static. Radiation and winds from nearby massive stars can blow away gas, carving shapes and triggering new waves of star formation. Supernova explosions can also play a role, sending shock waves through the cloud that compress the gas in certain regions, kickstarting the birth of more stars. This constant push and pull destruction feeding creation is part of what makes these